So in this problem, to find the acceleration of each block and tension in the string. So first we will go for the relation between accelerations of these blocks, these three blocks. Suppose this comes down with acceleration a1 and this comes down with acceleration a3 and this goes up, or you can take it comes down, obviously, whichever direction you take. If it is opposite to that direction, then it will give a negative answer. Later on, I am not putting any values for m1, m2, m3. So just to show you the method, that is m1g, this is m2g, this is m3g, and the tension in the string is T. This is T. So you know summation of T dot V here, summation of T dot A is equal to 0. So that will give minus T A1 minus T A3 plus 2T A2, that is equal to 0. See, A2 and 2T in the same direction. So therefore you get A1 plus A3 equal to twice A2. Now what is A1 equal to? See, A1 is M1G minus T by M1. What is A2 equal to? A2 is 2T minus M2G divided by M2, and this is A3 M3G minus T divided by M3. So now you have to just substitute these values A1, A2, A3 in this equation and find out. So that is a way. So M1G minus T by M1 plus M3G minus T by M3 equal to 2 into A2, means 2T minus M2G divided by M2. So you can find out tension from this expression, right? So you know G minus T by M1 plus again G minus T by M3 equal to get 4T by M2 minus how much? 2G. So there you get G plus 2G, 4G equal to T multiplied by 1 by M1 plus 1 by M3 plus 4 by M2. So T is this 4G divided by this 1 by M1 plus 1 by M3 plus 4 by M2. So as you find out T, so you can substitute T in these expressions for A1, A2 and A3 and find out the acceleration. Okay, right. Now suppose this type of a problem, this will be problem number 14, I guess. In problem number 14 there is an inclined plane having angle theta and there is a block on the plane. So it is moving with an acceleration A. So that's a smooth wedge. Okay, so smooth inclined plane or wedge, smooth wedge moves with acceleration A on floor so that the block doesn't slide relative to it. That means relative to this wedge the block doesn't slide. So find A, that means you have to find A. There should be a value of A for which this block will stick to the wedge. So block sticking to the wedge means actually this block will have same acceleration as that of the wedge. So this block is having same acceleration A as that of the wedge, then only there is no relative motion. Now if you look at what are the forces on the block, this is mg and this is the normal reaction, this is normal reaction and mg, and due to this resultant acceleration is this way. This is angle theta, so you can split it up into r cos theta and this is r sin theta, because these are the two axes. This is the direction of A acceleration. So you take here x-axis, this is y-axis. Actually what happens now, whenever you see the inclined plane, the first tendency will be splitting up this mg into mg sine theta and mg cos theta. Not for all problems, for this problem this is the ideal way of solving. Okay. So what you get, so in the y-axis there is no motion, so r cos theta is equal to mg. In the x-axis r sin theta is equal to ma. So from this a equal to g tan theta, right? A by g equal to tan theta. So a happens to be equal to g tan theta. Okay. Now we will learn a different concept, that of a spring forces. Now this is how a spring looks like. Okay, and this is what is known as the free length or natural length of the spring. Free length of natural length of the or natural length of the spring, that is the length when there is no force to stretch it or compress it. Now suppose sorry x is the extension in the spring due to force F. See, generally the mass of the spring is negligible, so there has to be force F from both ways. If there is force on one direction, the spring will run. So we don't deserve that. The spring is at rest and it's stretched, so this force has to be on both directions. Doesn't mean that it is 2F, it's still F. The stretching force of the spring is S. So if this is the natural length or L naught, this is the length L naught, so the extended length is L naught plus X. So L naught is the natural length of the spring. So there F happens to be proportional to X. So therefore F is equal to Kx. This K is known as the force constant of the spring. Force constant of the spring or spring constant. This is also known as spring constant. More is the value of the spring constant, more difficult it is to stretch the spring, because you see K is equal to F divided by X. So suppose there is a large force and for that the extension is very small, that means this K is very large, that means the stiffness of the spring is very high. So K denotes the stiffness of the spring. If K is less, then you can easily stretch the spring. However, this was the stretching force. Now similarly X is compression in spring due to force F. So this is how the spring is compressed. So again F is a force from both directions, so length happens to be L naught, natural length minus F. Then also F is equal to Kx, the same thing. That means the spring doesn't want its length to be changed. The spring wants to be in its natural length, so it will oppose. Whatever happens, if you want to stretch the spring will pull you, right? I mean the spring will oppose you from stretching it. If you want to compress the spring will again oppose you from compressing it. So spring wants to be in its natural length. Okay. Now, so this say let's solve some problems based on spring. So this 15th problem, this one. So for equilibrium, so this is the gravity here. For equilibrium, find extension in the spring. Find extension in the spring. Given K is its force constant. K is the value of the force constant of the spring. So it's what happens actually, its natural length was somewhat less. So it has extended by x due to this mass hanging. So now, so the force of the spring will apply a force on the block kx upward. See, block will apply kx to the spring to stretch it. So as per Newton's third law, spring will apply this force on the block, and this is the gravity force on the block. So if you consider the block, the free body diagram of the block, it is acted upon by two forces, weight and the spring force upward. Due to this, the block is at rest. So kx equal to mg. So the x equal to, or extension in the spring is equal to mg divided by k. M, this is a string, okay, G here downward, spring constant K. So in equilibrium, find extension in the spring. Find extension in spring and tension in the string. Tension in the string. This is the string. Okay. This is the first part of the question. Now there is a second part of the question which says find the acceleration. Find the accelerations of blocks A and B. I'll give names A and B of the blocks just after the connecting string is cut. That is, the string is cut just after that, to find the acceleration in the of the blocks actually. So now, so under this equilibrium condition, what are the forces and what are the accelerations? So obviously it is having zero acceleration. So let x be extension in spring. In equilibrium, okay, so on this block the force is kx. Now we can consider these two blocks as a system, right? So if you consider these two blocks as a system, what will be the weight? It's 2 mg. The weight is 2 mg. So kx happens to be equal to 2 mg. Therefore x happens to be 2 mg divided by k. Right? Now, okay, so find tension in the string. Oh, that was left out. So tension in the string, then you have to consider this block B only, free body diagram. So obviously block B is at rest, so tension is equal to mg. Or you could have found it in this way also. You could have split it up, and instead of taking A plus B system, you could have solved it in this way. This is the spring force kx, this is mg, and this is tension in the string, connecting string, and this same tension acts on this for block A and block B. So for A, what are the forces? So kx equal to mg plus t, and for B, t is equal to mg. So therefore you can combine the two, kx equal to 2 mg. The same thing we have done by considering this whole thing as a system. We can split it up and separately write the force equations or equilibrium equations of blocks A and block A and block B rather. Now find the acceleration of the blocks A and B just after the connecting string is cut. Now what happens after the connecting string is suddenly cut? So the string becomes slack, that is tension in the string becomes 0. So what is the force on this block? It is mg only. And what is the force on this block? So mg and kx. Now this remains kx, so this kx is 2mg. See, the spring doesn't I mean, just after you cut the spring, just after you cut the string, the spring for that moment remains in its same length. So same length means same force. The force of the spring depends on the extension. So it will having same extension just after the string is cut. Spring forces don't change suddenly. Why? Because spring lengths don't change suddenly. They have to move at a speed of light to do so, right? So it stays there, the length stays there. Gradually it will go down, or this goes up. Just at that moment the string length is same. Okay. Now, so what about the forces on block A and block B? Let's see. Block B, this is a force, and block A, kx 2mg. So what is the axis? See, so the force on block A is net force is mg upwards. So this is mg by m. So the acceleration is g upwards, g up, and this is having acceleration g down. This is the situation just after the string is cut. So just after string is cut, A has acceleration, how much? G upwards, and B has acceleration G downwards. Okay, just after string is cut, A has acceleration G upwards and B has acceleration G downwards, like shown in the diagram.